Well, this is my second time recording this video. First time, apparently I forgot to turn my microphone on, so 25 minutes later, we're doing this again. Okay, here we go. So, what we've been doing up till now is we've been applying the three primary trigonometric ratios. And the downside to that is that we can only apply those things when we have a right triangle. Turns out that not every triangle is a right triangle. Even if we look at it and we say, hey, that looks like a right angle, we can't make that assumption. So when we don't have a right triangle, these non-right triangles, they go by another name. They go by a term called oblique. So any non-right triangle is considered an oblique triangle. Think of it like an obtuse triangle where you have a largest angle that's greater than 90 degrees. That would be an example of an oblique triangle. Now, when we do have an oblique triangle, it means we can't use SOHCAHTOA, so it's not able to be reused or not able to be used. What we can do is we can apply this new law called the Sine Law. Now, it's called the Sine Law because we're going to be applying sine. However, we're not going to be doing it in the way that we've been doing it before. We can still use it to find sides and angles. That's useful. That's awesome. But the difference here is that it's the sines or angles of any oblique triangle. Oh, cool. Now, the thing is, there's a couple ways that we have to think about this. We have to remember how triangles are labeled. So if we have triangle ABC, where ABC are the angles, then the sides opposite of the angles have the exact same letter, but in lowercase. This is important to remember. Now, what the triangle that you see here, yes, it's an oblique triangle, but it's named ABC. Not all triangles are going to be named ABC. I could have a triangle, let's say P, Q, and R. Or I could have a triangle Bob, Linda, and George. A triangle is just a triangle. The names of the vector, or the names of the angles and the sides are irrelevant. As long as we're consistently using those sides and angles throughout the entire problem, it doesn't make a difference. There's not a problem at all. So let me just quickly erase this stuff so we have some space to work with here. Okay, so how do we actually apply the sine law? Well, first of all, we have to look at the data given. Now, the data given in the triangle is it's going to give us certain information in certain orders. So, for example, if I am given an angle followed by the next angle right beside it, followed by the side, this is what we call angle, angle, side. If I am given, let me just back that up a little bit, an angle followed by the immediate side to it, followed by another angle, I can apply it in the second set. Or finally, if I have a side, followed by a side, followed by an angle, that is also an application of the sine law. Or when we can apply the sine law, I should say. Now, let me just quickly get rid of that stuff. There we go. We have to be able to look at the triangle and realize that the direction of that doesn't actually matter. So, for example, I could have angle A followed by angle B followed by side A. Alternatively, it could be angle A followed by angle C followed by side A. Or start at C, C, A, C. So it doesn't really make a difference as long as we have that order. The direction doesn't actually make a difference. Oops. I brought that stuff right back. There we go. Alrighty. So once we know that we can use the sine law, we've satisfied one of these three conditions. How do we actually use it? Well, all we need to do is set up two ratios. All right, two ratios that are between its side and its angle. So any angle with its corresponding side will be one ratio. So for example, if I have this set, angle C with side C, and maybe I have the similar thing with A. I have angle A with side A. If I have 3 of those 4 pieces of information, I can calculate the 4th, right? Just by cross multiplying. Now, which ones you use, that'll all depend on the data that you're given. So when you set up this ratio, or these ratios, I should say, you want to set them up in a very specific way. Whoa, I think I just lost everything there. What just happened? I think I just scrolled down the whole way. Where did we go? We just lost a whole bunch of stuff there. Oh, 7.3, 7.4. There we go. 7.5. We're back at it again. Okay. So what we want to do is whenever we want to apply the sine law, we have to set up these ratios. Now, you can have any 2 of the ratios assigned to each other. It doesn't have to be all 3. Any 2 is fine. Okay. Now, when I'm looking for the sides, when I'm looking for some unknown side, then I want to set up the ratios so the sides are in the numerators. And then the denominator is always the sine of the angle that corresponds with the side. It's always the sine. How do I know this? Because it's called the sine law. Okay. If I'm looking for an angle, then the angle is going to be on the top and the side will be on the bottom. Why do we do that? Well, to be honest, a ratio doesn't actually matter what order you do it in as long as you're consistent with all of the ratios in the equation. So it doesn't really make a difference. However, doing this, the math will be a little bit easier to solve for, and it'll make your life a little bit easier to work with. So let's try it in this first example down here. We're going to use the sine law. I already got a couple sitting up here. There we go. We're going to use the sine law to determine the length of side Q. So where's Q? Q is right there. Now, what I want to do is I want to circle any ratio setup I have. So I'm looking for Q, so its corresponding angle is the angle Q. So there is going to be my first ratio. So I can write that out. So I'm looking for the side, so the side's going to go on the top. Q over 82 degrees. Not just 82 degrees, but the sine of 82 degrees. So I can get rid of that little degree sign. I don't actually need that. And I'm going to set that equal to any other full ratio that I have. Now, I need it to be a full one because this one is not a full one. I'm searching for the Q. So what other one do we have? Well, we have this 30 with its corresponding angle, which is the angle R. Well, there we go. So I put the side first, which is the 30, over the sine of the angle, which is 70. And now I got to solve for Q. Cross multiply, or more easily put, I just need to isolate for Q, which means multiply both sides by the sine of 82. So I have Q is equal to 30 times the sine of 82 over the sine of 70. Bam. And now we just solve. This is just calculator stuff. Just pump it into your calculator and you should end up with a value of, now it's to the nearest tenth, so we're going to say 31.6 centimeters. There we go. Next question is basically exactly the same. We have to look at it and make sure that we've satisfied one of the 3 setups. So what do we have? So do we have 2 angles? No, we don't have 2 angles, so it can't be either one of the top 2. We only have 1 angle. So let's see if we have side-side angle. Side, side, angle. Yep, this one works. So we can set this ratio up. Now let's circle the ratios that we have. I have this ratio with the D, angle D and side D. And I'm trying to find angle E. So that means I want angle E with its corresponding side, which is the 9. So there's the other one. Now remember, whatever we're searching for goes on the top. So since we're searching for angle E, that's the sine of E over its side length, which is 9, is equal to the sine of 85, the other ratio, over its side length, which is 16. Now we cross multiply by multiplying both sides by 9 here. So we end up with sine of E is equal to 9 sine of 85. Oh, we've seen this set up before. The sine of E means we've got to, oh, I forgot to put the 16 here. Oops. That means we got to isolate for E. So that actually means that we're going to have E is equal to the sine inverse of this whole thing. 9 sine of 85 over 16. And we end up with E being approximately 34 degrees. And that's it. All right, so it's still the same process. The only difference is whenever we're searching for an angle, just like we did when we were doing the trig ratios, we end up using the inverse trigonometric function. Okay, let's go down. Let's do a little bit more. Now, what you're going to see in the next few here is that we're not given a diagram. It's our job to actually create the diagram. Now, the diagram doesn't have to be accurate in terms of scale or size or anything like that, because we're just trying to paint a mental picture of this stuff. So it says we have a triangle DEF. So let's set up our triangle. So maybe our triangle looks like this. Okay, so you will be D, E, and F. Now it says side little d, so that's across from angle D, is 4 centimeters. You're going to be 4. Angle D itself is 49 degrees. It's 49. And angle E over here is 73 degrees. Okay, so we have to verify that we can actually do this. I have 2 angles, so we have to see if we satisfy one of the top 2. Angle, angle, side. Yep, there we go. That's the one we have. So that means we can use the sine law. All right, so since we can, we got to set up our ratios. So first, start by dealing with the side you're looking for. We're looking for side E, which is over here. So there's our first ratio. We have to include it as our first ratio. Then the other one is the only other ratio that we have both values for, which is D. So now we just got to set up the equation. We're looking for side E, so it goes on the top, over the sine of its corresponding angle, which is 73. And that's going to be equal to the side D, which is 4, over the sine of its corresponding angle, which is 49. We cross multiply again, and we end up with E is equal to 4 sine of 73. And that's going to be over the sine of 49. And there we go. Now from there, you should end up with a value of E is approximately 5 centimeters. Now it didn't give us a specific whether we should round or not, so I rounded it to the nearest whole centimeter. And there we go. The next question is largely the same, except now it's going to be looking for an angle. So let's draw our triangle again. This time we have triangle ABC. So let's do it like this. So let's put A down here, B up here, and C over here. It tells me side B is 5.4 centimeters. So you're going to be 5.4. Side C is 6.2. And angle B is 56. So what are we looking for? It says find angle C. So we're trying to find angle C over here. So we got to look at the ratios we can set up. So first of all, we're looking for angle C, so that's got to be the first one. Can't really get around that. And then finally, angle B with its corresponding side, we have a full set right there. So there's our setup over there. So let's set up our ratios. We're looking for an angle, so that means the sine of angle C is going to be on the top. Sine of angle C over its corresponding side, which is just 6.2. And that's going to be equal to the sine of 56. And that's going to be over 5.4. Now we solve for sine of C again. Sine of C is equal to 6.2 times the sine of 56 over 5.4. And we got to solve for C. So that's going to be sine inverse of this whole thing again. 6.2 times the sine of 56. And that whole thing is going to be over 5.4. So all said and done, C is going to be approximately equal to 72 degrees. All right, not too bad. Let's go to something a little bit more complicated. So this question is asking us to solve this problem. There's actually more than one way to solve this problem, and I'm going to show you them both just so you can see them. So it says determine the diameter of the ice cream cone shown below. So the diameter is the distance across here. Now we can look at this and we can see that we have a triangle. Whoops. We're going to undo that. We're going to try again. Oh my goodness. That's slightly better, but not much. So if I'm looking at this triangle, I think I'm going to redraw it over here. That's slightly better, but not much. We can see that the inner angle down below here is 36 degrees. We can see that this is 17, and so is this. Oh, wait, we got two equal sides. That tells me this is an isosceles triangle. It also tells me that the inner angles at the end are also equal. Oh, we got lots of information going on here. So looking at this, can we actually calculate those side lengths? Of course we can, because we have 36 degrees here, and we know a whole triangle is 180 degrees. So the leftover from 180 minus 36 are these two angles. So I just figure out what's left over and divide it by 2, and there are my angles. Okay, so let's try that. So let's label this triangle first of all, just so we can kind of give it a good name. So this is going to be triangle A, B, and C. So looking at this, we can see that angle B is going to be equal to angle C because the isosceles triangle theorem. Great. Now, can I calculate angle B and C? Yeah, I can. So let's say we have angle C is going to be equal to 180 minus that 36. That's going to leave whatever's left over for both those angles. And since they're the same size, we're going to divide that by 2. And what you're going to get is a value of 72 degrees. So now we know the length of both of those sides. Interesting. So now we look at it and we say, well, can we use the sine law? This is clearly not a right angle triangle. So can we use the sine law? So do we have angle, side, angle, or what are the other ones? Oh, angle, side, angle. What's the other one? Angle, angle, side. Or side, side, angle. So let's see what we got here. Now we know we're calculating for a side length, so we want to use one of the first two. So do we have angle, side, angle? There's an angle 72. There's a side 72 and an angle 36. Yeah, we can actually do this. Okay. Technically speaking, we could have done an angle, angle, side as well because we could have just went the other direction. Angle, angle, side. So it works. So we can set up the sine law. We just have to set up the right ratios. Now we know we're looking for side length A over here. So there's our first ratio. And then we could set it up with either C or B. So that means angle C with its corresponding side length of 17. Let's just set up the math now. We're looking for side A. And that's going to be over the sine of its corresponding angle, which is 36. And that's going to be equal to side C, which is 17, over its angle, sine of 72. Now we just need to solve for A. So we're going to multiply both sides by sine of 36. So A is equal to 17 sine of 36 over sine of 72. And when we calculate this, we get a value of approximately 10.5 centimeters. And that's it. That's the whole question. Now, I did say that there was another way. Now, imagine for a second that I redraw this triangle one more time. There's our diameter. Now, we know that that angle is 36 degrees. We know that it's an isosceles triangle. We know that each angle over here is 72, right? 72 degrees and 72 degrees. Now we labeled the triangle A, B, and C. But this is an isosceles triangle. What that means is that if I cut it in half, if I went right from the middle here, and I went right down the middle, it is going to be symmetrical on both sides. And since I cut it right down the middle, I just created two right triangles. So let me redraw just that right triangle. Let's call this vertex D, just so we can label this. So that means that I have a triangle that looks like this. A, B, and D, which is a right angle. And we know that this is 17. We know that this is 72. We also know the angle down here as well. We know that it's half of 36, but that actually doesn't matter. We don't need that. We just need to calculate this side up here. Now, when this whole thing is called the diameter, what is half of the diameter called? Well, that's just the radius. And we know the diameter is equal to 2 times the radius. So if I can find the radius and double it, that means I can find the diameter. So let's just call this R, right? Because we know we're trying to calculate the radius. Okay, so how do I do this? Well, we only have the one angle here that we're looking at, so let's label our triangle based on that angle. That would make this one opposite, this one, hypotenuse, and this one up here adjacent. So what does that mean? It means that I have the hypotenuse, but I'm looking for the adjacent. So AH, that's CA. So I can actually use my primary trig ratios because I'm on a 90-degree or right angle triangle. So I could say the cos of 72 is going to be equal to A, which is R, over 17. Now, R is equal to the 17 times cos of 72. So the radius that it's going to give you here is about 5.25. Now, since we said the diameter is 2 times the R, D equals 2R, which is going to be equal to 10.5 centimeters again. We got the exact same answer. So now I want you to look at these two sets of work. On this side here, we had to draw a whole new triangle. We had to set up all the ratios and everything like that. Then we had to do more calculations and an extra calculation at the end just to make sure we got to the diameter versus the sine law, which was 2 steps and we're done. So if you can apply the sine law and it makes sense, then you probably should, because chances are that it's going to make the math a little bit easier and easier to work with. So that, my friends, is the sine law. The next one, we're going to push it again to learn some new rules to apply the cosine law. That's it for now.